So the next topic is a very important law called Pascal's Law in fluid statics. Pascal's Law. So what is Pascal's Law? Let me first try to explain with this visual diagram. So here, this container is filled, completely filled with some fluid, hydrostatic fluid. It could be water or any hydrostatic fluid, and and several pressure gauges are attached to measure the pressure. The fluid pressure. So these are the pressure gauges which can measure the fluid pressure inside this container. And here this end you can apply some pressure. So for example, Pascal law simply said if you apply 5 pounds, say 5 pounds of pressure here by exerting, by squeezing it, all this pressure gauges will show exactly 5 pounds. So that's why any change in the pressure applied to an enclosed incompressible liquid is transmitted undiminished equally to every portion of the fluid and to the walls of the container. Okay, so that's basically Pascal's law. So again, if you apply five pounds of pressure here, all these pressure gauges will show exactly 5 pounds of pressure. So pressure, any change in pressure, right, applied to the given fluid, it will be equally transmitted in all directions. So that's the Pascal's law. And what's the what is the main application of Pascal? So Pascal's law's main application is the hydraulic lift. Okay, so you can lift actually, uh, uh, you know, 4,000 pounds car just by using, say 200 or 200 pounds of force. So and that is used in, uh, you know, that is used in hydraulic lift principle. So let me show you the derivation. So, what's the working principle of hydraulic lift? So, let me explain here briefly. So, it works under Pascal's law. So, remember in previous slide, Pascal's law simply says, right, if you apply any pressure on an enclosed system fluid, that pressure will be transmitted equally in all directions. So here you apply some pressure, you apply some force in this narrow tube here, and it generates some delta p, say. So if you apply some force here, it creates some change in pressure in this narrow tube, and that change in pressure will be equally transmitted based on you know equally transmitted all direction, right? And not just against the wall. It's equal everywhere, right? Based on the Pascal's law, and is equal to, so let's say this side of the tube is 1, this side of the tube is 2. So and pressure is force over area. So the pressure here generated in this narrow tube is force 1 divided by area 1. Area is cross-sectional area is different, must be equal, right? Any change in pressure you exert will be equally transmitted in all directions. So it has to be equal to the pressure transmitted in this wider tube as well. So here the force generated here is, let's say, F2 over A2, right? And so since they are equal, so we like to find out, let's say this is F1 and F2. We like to find how much force will be generated here. So let's find out. F2 is equal to A2 over A1 times F1. But since these are circular cylindrical tubes, so area is pi r square. So based on that, pi r2 square over pi r1 square times F1, right? And pi will cancel out, and F2 is r2 over r1 square F1. So that's the main working principle of any hydraulic lift. As you can see, R2 is greater than, this is wider tube, R1, all right, you can clearly see F2 is greater than F1, right? You can generate a much stronger force in this wider tube, wider piston compared to here. So if you apply, say, say here 100 pounds of force, if I exert 100 pounds of force, it can create thousands of pounds of force on this wider section of the piston, and that is enough to lift a heavier object. So that's the main working principle, you know, of the hydraulic lift system. So our last topic on fluid static is buoyant force. So basically, in very simple word, buoyant force is the lift generated by the surrounding fluid. So because, as you know, right, any object, always weighs less in liquid uh, compared to air, right? And that loss of weight or that lift is generated because of buoyancy. And what's the main origin of buoyant force? As you know, right, the hydrostatic pressure increases with depth. So these are the pressure forces acting on any object when you submerge it, into any liquid or fluid. So all the horizontal forces will cancel out, it doesn't matter. But there's a net lift force, there's a net upward force, right, acting on the object. And this is the cause of, buoyant force. That net lift force, because of the difference in this pressure force, acting on the bottom and acting on the top, is the origin of buoyant force. This is basically the buoyant force, which we can calculate using a law called Archimedes principle. So examples are, so buoyant. This is an example of buoyancy compensator jacket. So the divers need that. The deep ocean divers actually need that because you have to compensate the buoyancy acting on your body actually. So you will have to increase or decrease the buoyant force, during the diving. So the next is Archimedes principle. So Archimedes principle, I will just state it. When a body is fully or partially submerged in a fluid, a buoyant force is exerted on the body by the surrounding fluid in upward direction. This force is its magnitude is exactly equal to the weight of the fluid that's been displaced by the body. Okay, so let me show you this example. So Archimedes principle says this. So for example, this the weight of this object weighs 7 pounds, right, in air. Now let's submerge that object here, right, and so this will displace. See, this object will displace some of the liquid from this container, and let's collect it in a separate bowl. So and again measure the weight of the given sample in this liquid, and it weighs say 4 pounds. What's the loss of weight? So loss of weight is 3 pounds. And what Archimedes principle exactly says is the loss of weight, which is equal to the buoyant force, is exactly equal to the weight of the fluid that's been displaced by the liquid, by the object. That's the Archimedes principle. Okay. So here the loss of weight is 3 pounds, which is buoyant force, which is because of buoyant force, has to be exactly equal to the weight of the fluid that's been displaced by this object, which is collected in a separate bowl, which is 3 pounds. So in conclusion, mathematically, right? So buoyant force is given by the Archimedes principle, and it is equal to the density of the fluid and the volume of the fluid that's been displaced by the object, right? And gravity, okay, and which is also equal to the loss of weight. So loss of weight of any object in liquid is exactly equal to the buoyant force. Okay. So some more explanation of Archimedes principle and buoyant force. So for example, here in this first example, if an object is completely submerged, right? If an object is completely submerged, how would you find the buoyant force acting on this object? So it's easy. Just use the Archimedes principle. So the volume of the object is exactly equal to the volume of the fluid that's been displaced by the object, right? Because it's why? Because it's completely submerged. So, and if an object is completely submerged, it's easy. The buoyant force is the density of the fluid times the density of the volume of the fluid displaced times gravity. But volume of the object is exactly equal to the volume of the object. Volume of the fluid displaced by the object is exactly equal to the volume of the object itself, right? Because why? Because it's completely submerged. Now let's see the second case. Second case is now what happens if an object just float, partially, just like an iceberg. So how do you find the buoyant force. So buoyant force in this case, so you first need to find out how much volume is submerged underwater, under a fluid. And once you find that out, then you just put it here. Now your volume of the fluid displaced is exactly equal to how much volume which is under water, under the submerged under fluid. So that's how you can calculate, you know, the buoyant force in two different cases. So whether an object float or sink depends on how much buoyant force is exerted by the fluid. So for example, if the buoyant force is less than the object, weight of the object, then it will always sink. If the buoyant force is greater than the object, it will float up. And if the buoyant force is exactly equal to its weight, then it's called neutral buoyancy, right? It's exactly neutral, static, neutral buoyancy. So here's some example. So in this all this example, these objects are floating easily on this fluid. Why? Because of this condition. If the density of the object is less than density of the surrounding fluid, it will always float because it will always create a buoyant force. The buoyant force will be always greater than its weight, and eventually it will balance its weight. So this condition, first condition, is if the density of the object is less than density of the fluid, the object always floats. So here's some examples. So this metal coin has less density compared to the mercury, because mercury, even if it is liquid, it has a very high density, 13,600 compared to 8,000, the metal density, right? So it will always float because this metal coin will get enough buoyant force so that it can balance its weight. So same example with this ice cube, because ice cube density is slightly less than the water density, so then it partially floats because it gets enough buoyant force to balance its weight. Here's these people are floating without any floating device, and the reason is these examples are somewhere in Dead Sea, some in Middle East, and it's called Dead Sea because this lake has too much salt concentration. So the human density, our human density, slightly less than the density of the salt water. So that means so you can have enough buoyant force, so that will lift your body easily. So okay, these are some examples. So now next example is, now if the density of the metal here is way bigger than the density of the sea water, but the ship, which is made from steel, can float easily, and the reason is because of the shape. Look at the shape. The ship hull, right, is designed so that it's almost hollow, right? So it can displace more and more water, so the ship is defined, ship or boat is designed so that uh, you know it can displace a huge volume of water. So that's the main idea, so that it can you know so the buoyant force acting on it is huge, because from this Archimedes principle, the buoyant force depends on how much volume it displaces, right? The volume of the body, right? Volume of the object, volume. So that's the main physics behind that. So once the ship is settled down, right? Initially, its buoyant force is less than its weight. So it try to sink, but at some point it will displace enough water so that it has enough buoyant force, so it can counterbalance its weight. So that's how the ship can easily float. It has to do with the volume, how much volume the boat can displace. So same thing applies to the helium-filled balloon as opposed to the air-filled balloon. Helium-filled balloon can float up because of this condition, right? Because the helium is much lighter than air, so its force of gravity here is less than the buoyant force it gets, right? And remember, buoyant force depends on the volume of the balloon, right? As opposed to air-filled balloon. So air-filled balloon is so condition is buoyant force is same actually. Its buoyant force is same because why? The volume is same, right? If you fill with same amount of volume, but the air is much heavier than helium, right? So it can't balance, the buoyant force can't balance its weight of force of gravity. So that's why it can't float up. So that's the main physics behind that. And here's the situation, if you can see all these pressure forces acting on this is an example of hot air balloon again, and all these vectors, this with arrow are the pressure forces acting on this helium, air hot air balloon, right? So as you can see, the pressure force acting on this surface bottom is slightly bigger than stronger than pressure force acting on the top. And then the net result is this. The net result is you have an upward force acting upward in this direction, which is the buoyant force, and which is greater than the force of gravity. That's why hot air balloon rise up.